So now we've reviewed the Schrödinger equation. Next thing we want to say is the most important solutions of the Schrödinger equations are those energy eigenstates, stationary states, and let's just go through that subject and explain what it was. So I'm going to start erasing here. And so we're going to look at stationary solutions. Now, I've used this wave function with a capital psi, stationary solutions, for a purpose, because I want to distinguish it from another psi that we're going to encounter very soon. So stationary solutions, and we'll take it from now, assume V is time independent. The case is sufficiently important that we may as well do it. So in this case, the Schrödinger equation is written as IH bar d psi dt, and we write it with something called an h hat acting on psi, and h hat at this point is nothing else than minus h squared over 2m second derivative with respect to x plus v of x. We say that h hat is an operator acting on the wave function psi on the right. Operator acting on that. What does that mean? Basically, when we say an operator acts on some space, we mean that it takes elements of that space and moves them around in the space. So you got a wave function which is a complex number that depends on x and t ultimately, and then you act with this thing, which involves taking derivatives, multiplying by v of x, and you still got some complex function of x and t. So this is called the Hamiltonian operator, and it's written like that. This Hamiltonian operator is time independent. So what is a stationary state? A stationary state of, so the way it's defined is as follows. A stationary state, of energy E, which is a real number, is a psi of x and t of the following form. It's a simple form. It's a pure exponential in time times a function that just depends on x. So it's a pretty simple object. So what is it? We say that this is a stationary state, e to the minus I et over h bar psi of x. And this psi is in purpose different from this psi, doesn't have the bar at the bottom, and that signals to you that that's the time-independent one. So this also belongs to the complex numbers, but doesn't depend on time. So it's called stationary because, as it turns out, when we will compute expectation values of any observable on this state, in this stationary state, it will be time independent. In particular, you know one thing that is observable is the probability density. And when you look at that, look at this, you have psi star times psi. Since E is real, this phase cancels. This is really a phase because E is real. Therefore, psi star psi, the E cancels, and all the time dependence cancels and goes away. Same thing here for the J. The x derivative over here doesn't do anything to that phase. Therefore, the phase e to the I et over h bar cancels from there too, and the current also has no time dependence. So this will be the case for any operator that is called a time-independent operator. It will have time-independent expectation values. So you can ask anything about some familiar operator, energy operator, momentum operator, angular momentum operator, all the famous operators of quantum mechanics, and it will have real expectation values. So as you know, you're supposed to now plug this into this equation, and it's a famous result, and let's just do it. Plug back into the top equation, so we have I h bar. The ddt will only act on the phase because the psi has no time dependence. And on the other hand, on the right-hand side, the h has nothing to do with time. And therefore, it can slide through the exponential until it hits psi. So here you have h, well, I'll put the exponential in front, h on little psi. So we multiply here, and what do we get? Well, the h bars cancel, the I and minus I gives you 1, you get an e in front, so you get e times this phase, psi of x, and the phase is supposed to be here, but I cancel it with this phase as well, and I get on the right-hand side h psi, that I will put it as a left-hand side, and this is the time-independent Schrödinger equation. So far, this is really a simple matter. We've written a solution that will represent a stationary state, but then this energy should be such that you can solve this equation. And as you've learned before, it's sometimes not so easy to solve that equation. So what do we want to say about this equation? Well, we have a lot to say, and a few things will be pointed out now that are very important. So we have a differential equation now. This differential equation has second derivatives with respect to x. Now it has no time derivatives. The time has been factored out. Time is not a problem anymore. This equation, in fact, looks quite real, in that it seems that psi could even be real here. And in fact, yes, there's no problem with this psi being real. The total psi just can't be real in general. And, but this one can be real, and we'll consider those cases as well. So things that we want to say is that this is a second-order differential equation in space. So second order differential equation in space. You could write it here. The h operator has partial derivatives, but this time, you know, might as well say that this is minus h squared over 2m, the second psi dx squared plus v of x times psi of x. Because psi only depends on x, so might as well write it as complete derivative. So second order differential equation. And therefore, the strategy for these equations is a little alternate to the Schrödinger equation. We said in the Schrödinger equation, if we know the wave function everywhere, you know it later. Here, if you know it at one point, the wave function, and you know the derivative at that one point, you have it everywhere. Why is that? Because that's how you solve a differential equation. If you know the wave function and the derivative at the point, you go to the equation and say, I know the wave function, then and I know the first derivative, then I know the second derivative. So a little later, I can know what the first derivative is. And if I know what the first derivative is a little later, I can then know what the wave function is a little later, and you just integrate it numerically. So you just need to know the wave function psi of x0 and psi prime at x0 suffice for a solution. When V is regular. That is, if V is not too complicated or too strange, because you can always find exceptions. You have the square well potential, and you say, oh, I know the wave function is 0 here, and its derivative is 0. Does that determine the solution? No, because it's infinite. There's no space here, really, and you should work here. So basically, unless V is really pathological, psi and psi prime are enough to solve for everything. And that actually means something very important, that if psi is equal to 0, at x0 is equal to 0, and psi prime at x0 is equal to 0, then under these regular conditions, psi of all x is 0. Because you have a differential equation in which the initial value is 0, the psi prime is 0, and you go through the equation, you see that every solution has to be 0. It's the only possibility here. So what happens now is the following, that you have a physical understanding that your wave function, when it becomes 0, it may do it slowly, that it's becoming 0, but never quite being 0. But if it's 0, it does it with psi prime different from 0, so that the wave function is not 0 all over. So this is a pretty important fact that is useful many times when you try to understand the nature of solutions.